Look closely at the surface of these Southern African beadwork panels. Beyond the vibrant colors, there is an unyielding precision to how each piece locks. Overlaid with these algebraic classifications, the beadwork functions as a strict geometric data set. We are going to examine these panels entirely through the lens of abstract algebra and group theory. In this tradition, mathematical knowledge is encoded directly into the physical structure of the craft, an embodied literature that records complex logic in 3 dimensions. In a 2001 study, researchers Rayda Becker and team documented that these cultural artifacts operate under complex algebraic roles, executing them with flawless consistency. These artisans were practicing geometry in action, systematically mapping the laws of symmetry through the tactile medium of glass beads. To understand the algebra at work here, we first have to define an isometry. An isometry is a rigid geometric motion that transforms a pattern into an identical copy of itself without any stretching or distortion. We can isolate a single motif from the beadwork to serve as our baseline mathematical unit. The most basic rigid motion is translation, sliding the shape along an axis to repeat the exact same form elsewhere. Next, we have rotation, which spins the shape around a central point, and reflection, which perfectly mirrors it across a dividing axis. The fourth and most complex rigid motion is the glide reflection. This requires sliding the shape a set distance and then mirroring it, executing 2 operations in one fluid step. In abstract algebra, a set of symmetries forms a group only if it passes 4 strict mathematical tests. Closure means combining any 2 valid motions always produces another valid motion within the system. Identity is the state of doing absolutely nothing, leaving the shape exactly as it is. The inverse property dictates that every action can be perfectly undone, reversing the motion to return the shape to its exact starting point. Finally, associativity requires that the sequence of how you group these transformations together does not change the final resulting pattern. These physical bead patterns satisfy every axiom of the algebraic group, existing as literal, tangible proofs of abstract symmetry. When a motif is repeated at regular intervals along a single one-dimensional line, it creates what mathematicians call a frieze pattern. These linear structures appear frequently in traditional African attire, defining the repetition of colored bands along necklaces and belts. In algebraic algebra, there are exactly 7 distinct symmetry groups possible for a one-dimensional frieze pattern. The 2001 study confirmed that Southern African beadwork contains physical examples of all 7 possible groups. The most common classification found is R2MM. It achieves a high degree of visual balance by utilizing mirror lines on both the vertical and horizontal axes, creating the rarer glide reflection patterns, classified as R1G and R2MG, demands intense spatial reasoning from the creator. To execute a glide reflection by hand, the artisan must mentally cut a shape in half, shift it along a continuous vector, and invert it in physical space, all without the aid of graph paper. Executing all 7 one-dimensional groups shows that these artisans were systematically exploring the absolute limits of geometric possibility along a line. By introducing a second non-parallel vector, the canvas expands from a single line into a 2-dimensional plane, producing what are known as planar or wallpaper patterns. Mathematics dictates there are exactly 17 possible planar symmetry groups. The historical beadwork collections successfully map at least 7 of them. The panels even exhibit elusive 3-fold and 6-fold rotational symmetries, configurations that are exceptionally rare in craft traditions globally. Operating on a 2-dimensional plane introduces a strict geometric law, the crystallographic restriction. To preserve perfect symmetry without leaving gaps, 2-dimensional periodic patterns can only be rotated at increments of 360, 180, 120, 90, or 60 degrees. Attempting a 5-fold symmetry, a 72-degree rotation, is mathematically impossible for a continuous periodic grid. The shapes will inevitably overlap, breaking the pattern and leaving empty space. The beadwork consistently aligns with this absolute restriction. The indigenous artisans intuitively recognized the boundary of the plane and did not break its geometric law. Theoretical mathematics assumes perfect conditions. Physical craftsmanship has to contend with material constraints. Glass beads are an imperfect medium. They vary wildly. Some are spherical, some are ovoid, and their sizes fluctuate depending on the color of the glass. To build their grids, the weavers utilized two distinct threading techniques, aligning the beads in straight vertical rows or staggering them in a shifted brick wall formation. When the irregular physical dimensions of the beads clash with the rigid mathematical ideal of the pattern, the structure of the grid inevitably warps. This leads to an unintended irregularity. While a woven triangle may aim for a perfect 60-degree angle, the uneven mass of the beads forces the physical edges to bulge outside the mathematical lines. These deviations are not errors in calculation. They are the physical residue of engineers actively calibrating material variables to approximate a perfect mathematical ideal. The use of these complex principles spans multiple tribes, regions, and centuries. This consistency points to a deeply embedded, shared geometric literacy across Southern Africa. The visual structures of these panels establish a direct equivalence between the physical artifacts and algebraic equations. The 2001 study concluded that the creation of these symmetrical designs directly mirrors the inductive and deductive thought processes of a formal mathematician. Behind every theorem represented here are the hands that actively calculated it, threading piece by piece to build the matrix. This demands that we re-evaluate how we define, recognize, and value scientific and mathematical literature. Advanced mathematical reasoning doesn't require paper or a chalkboard. It can be calculated, proven, and recorded entirely in the tension of thread and glass.